Okay, thank you very much. We already have a few questions coming in Slack. So the first one is Murat Demirbas. Does this allow pipeline of consensus instances?
Hello, yeah, so that's a good question. And then in our evaluation, in the current implementation, we don't have a pipelining. And then in the paper, we outline some steps that we can do pipelining. Yeah.
So does it, just to complement his question, does it mean you're not doing pipeline in multiplexers in your multiplexers implementation either?
Okay, that's a good question. So when I say that no pipelining, mean that no pipelining in the current Rabia implementation. And when we compare the multiplexers and ePexels, both of the system, the pipelining was enabled.
Okay. So another question, also from Slack, and I think the person is not a panelist. It's Harold from KTH. How does Rabia gain performance advantage over multiplexers with both higher message complexity and more message delays in the fast path? One could imagine that our replicas would be heavily loaded and therefore perform worse than multiplexers, where only the leader might be bottlenecked.
Yep, that's a very good question. And I would say that I totally agree with the first part. In our evaluation, we observed that the bottleneck is that when they do like this serialization and deserialization. And then actually that's why we perform better than multiplexers, because all the replica, they can handle the communication with clients. But like when we push to very high workload, then in multiplexers, only the leader can handle this communication. And then in fact, that's also why ePexels were performing better with compared to multiplexers.
Okay, so next one is a panelist, Sudong Sun.
Oh,
please
yes.
Go ahead, Anish.
So if I understand correctly, Rabia should be a binary consensus algorithm that outputs 1 or 0. But if that's the case, how do we apply it to like log-based SMR, where replicas need to agree on the order between the requests? So yes. In other words, like how to convert it to like a multi-value consensus algorithm?
Yes, that's a very good question. So that let me kind of summarize the question. First, BNO, the original paper is binary, only 0 and 1, but for state machine replication, it's a general value. And then how we did that is actually we use like BNO's algorithm as a kind of decision, say that can we agree fast on this slot? So if you read the paper, actually there are two phases. The first phase is that for all the replica to exchange the values or the request for this slot. And then the next phase is that to run BNO, say that can we agree on certain order? And then if we can agree, then that's a good. We are on the fast path, like three message delay, then we can agree. If not, then we need to use some other mechanism to agree on the order.
Nice.
And yeah.
Thank you.
Yeah, thank you.
So we have a few more questions in Slack. So the next one is Edward Tremel from Augusta University. How do you decide when to fail fast and issue a NoOp instead of trying to issue a client request?
Okay, so that's related to this like two-phase thing I mentioned, and the idea is kind of like in the exchange phase, if the majority or like even super majority observe or like they propose the same client request for this slot, then we can agree on that. And then what happens if that each replica propose a different request for this slot, and then that in our design in the second phase, everyone will actually propose 0, and then that's how we can achieve that the fail fast thing. So that in summary, in the first phase, if most of the replica receive the same proposal, then they can agree on very fast. And then in the first phase, if that most of them propose different proposals, then in the second phase, when we use BNO, then they will fail fast. And then in our experience, both these two cases that like happen around like 98% of the time.
Okay. So don't have posted a question here, but I'm not sure it is exactly what you asked before.
Yes, I think it's the same question. Yeah.
So John Osterhout from Stanford, in your graph of different zones, why did Rabia latency drop as load increased?
Okay. Actually, let me check the figure again. So the Rabia, the throughput. Okay, let me see. Oh, okay. So yeah, the latency drop, it's because the way we do batching. So that when under the low workload, it's that we need to wait until timeout is triggered. I think that I forgot like how many milliseconds. Then that we create one batch for this slot. But then when the high workload, when we increase the number of clients, so that we can increase, I say, 20 clients requests, and then we will use that as one batch. So actually the latency drops.
Okay. We have time for another one. So Harold, you mentioned serialization of all client requests at the leader of multiplexers. Doesn't all replicas have to serialize the requests if they have to propagate the client requests to each other?
Sorry, which question from whom? So I'm reading Slack here as well.
The very last one. You want me to read again, or?
No, I'm reading it. Thank you.
Okay.
Oh, okay. So yes, but like let's say that because when we do the maximum workload, then it's like 300 to 500 clients, and for multiplexers, it's that like the leader need to communicate with all the clients, and then I think that compared between like multiplexers and Rabia, the workload of a single replica is larger than all the other. So it's true that all the replica in both multiplexers and Rabia, they do need to do certain of a type of a serialization and deserialization. But in terms of multiplexers, the leader's workload is much higher than like other servers in when running Rabia.
Okay. So I have a question for you. So sure. Would it make sense to combine these optimizations with a protocol that like epoxes, for example?
That's a very good question. So I would say that epoxes is more similar to the multiplexers, where you have the idea of a command leader. And then actually we found out that especially in our target use case inside a single data center, then epoxes bottleneck is like do this like the dependency check. And then when we have like certain amount of batching, and then when we have like say 100 clients, then the dependency check takes like almost like 80 milliseconds. And then we found that that's like what makes our epoxes actually like not performing as well as we thought. Yeah.
Okay.
Yeah.
Excellent. Okay, so we don't have any further questions, and at the same time, I guess we reached the end of this session. So I'd like to thank everyone, presenters, and also people in the audience asking questions for these very interesting discussions. Thank you very much. And okay, so you guys have a good time for the next session. Bye, everyone.
For that video. For this mirror, we have Haochen, who is the first author of the paper available to answer questions for us. Let me kick it off with a question here. Oh, actually, Inno is ready to, why don't you just lead off again, and we'll have you ask your question, and I'll save mine for later.
Okay, thank you. Then, yeah, I will go first. Yeah. Hello, Haochen. Thanks for the great work. Yeah. One interesting idea that I found in the presentation is that your work use NoOp to kind of guarantee the high progress rate in case of the the replicas cannot decide the specific operation. But I think, yeah, I understood that it makes the servers go faster when in such case. But in terms of the client perspective, if a client send a request, but if it is decided as NoOp, then the client should go for the should retry the request to be processed properly, right? Then
I see. Yeah. Do you have please finish your question. Yeah.
Yeah. So I wonder if the NoOp happens quite often, then it may cause some significant throughput degradation from the entire system perspective. And how often do you observe the NoOp depending on the configuration, like experiment setup? Yeah.
Yeah, I see. Well, that's a very great question. So maybe we haven't clarified that part in the presentation. So in fact, if a consensus instance decides a NoOp as the final agreement, it actually so the servers broadcast NoOp to themselves without telling the client here is a NoOp operation. So in other words, the NoOp is not visible to the clients. So the clients are still waiting for the next decision. And so after servers decide this slot to be assigned as NoOp, servers will continue to work on the next slot. And since it's already a little time has passed, so more pending requests are congregated in the main heap of pending requests. So servers has more high ability to reach a non-NoOp agreement. So, and then after reaching that concrete value, multi-value agreement, one of the servers can send such response to the client. So to summarize, NoOp are invisible to clients as only Rabia's construct. Yeah, maybe.
So,
yeah.
So the client who sent the very specific, the particular request, which was decided as NoOp, then it should wait for the timeout and resend the request, right?
So when servers decide the NoOp, clients will not know that. Servers will continue to work on and decide the next non-NoOp operation and send it back to clients. So clients will continue to wait until timeout if there is never a response come back.
Right. So the client will just keep waiting for the response, but it will not get any response because
you will not get NoOp.
And eventually the timeout will happen, right?
Yeah, yes.
I see.
Otherwise, that's not ideal. Like we don't want timeout to happen. We just want to get back to clients as quick as possible.
I see.
So, yeah.
Okay, thank you. Thank you for the answer. Yeah.
It looks like, Andrew, you have a question?
Yeah. So I wanted to ask about how you tune when you decide to produce one of these NoOp things in a slot, not to just belabor the point about NoOps the whole time, but the reason I'm asking is I was thinking an alternative design would be to instead trigger another round of the same protocol trying to reach agreement on the same slot. So you'd have sort of parallelism that way, like you might have parallelism in speculative Paxos, but instead just for the same slot. Just curious what your thoughts were on that.
Yeah, we try. So I remember one time, I tried to implement something in parallel, multiple instance of consensus instance going on, trying to decide. But somehow that complicated the structure a lot, and we don't get concrete performance increase. But the notion of NoOp exists the first day the professor told me this. So it has been there the first day.
And I guess just to clarify, how did you decide when you issue the NoOp relative do you just give up after, when do you know to give up, basically? That's the question.
Right. Yeah. So basically NoOp is meaning all the servers want to go to the fast pass and decide the slot in 3 message delays exactly. So if there's no no majority of replicas receive a single value, then all these replicas will decide on NoOp. So, and the way to go to the NoOp path is a fast path. It's as fast as the normal fast path, like the path that they decide on concrete value. So if no majority of servers, see there's a majority value, they come to the NoOp path.
Okay, I can either cede my time or I have another question if Jason doesn't mind.
I'll ask one question.
Okay.
Because so one of the questions I have is this paper pushes on the notion of simplicity, and that's pretty hard to define. But one thing I think our community underestimates a little bit is operational simplicity. That is the observability of the system, the debuggability of the system. When something goes wrong, how quickly can I understand and figure it out? And in that sense, I wonder if a leaderless protocol is harder to operate than a leader protocol, because I can't go to one place and figure out what's happening in the system. I have to look at what's happening across a set of replicated nodes, which is inherently harder. So I wonder if you had any thoughts about that.
Yeah. So in practical sense, I would say our code base has like 2,000 or less than, around 2,000 lines of code. But for ePaxels and multiplexers, they're a few times larger than us. So if we want to do some kind of debugging, maybe their system are hard to debug. And also, like for multiplexers, there and the ePax and like a raft, as mentioned in the video, they need to have some kind of auxiliary protocols like log compaction, snapshotting. So that kind of thing also kind of like contribute to the complexity of the code. So so the simplicity of randomized protocol, I guess it has twofold meanings. One is like it has not so many numbers of lines, even though you have to read sometimes like logs from multiple servers that produce some kind of a log. You have to carefully examine them. But I would say that's not a big deal. And also the second part is that the randomized protocol don't have so many auxiliary helper functions. So that's another part of simplicity. Yeah.
Yeah, I hear what you're saying. And it's a little bit of a different observation that just, I think you're underestimating a little bit the difficulty of aggregating multiple logs.
Okay.
But then also the randomization means that there isn't necessarily one code path that each request is going to take. So I think that's one reason that protocols like Raft have been successful. It's not just it's easy to code, but also it's pretty easy to understand. So, but I agree, it's really hard to evaluate this. I don't know any way to look at this other than trying to build 2 industrial strength systems and asking the programmers which was more painful. I think we have time for one last question. Andrew, do you want to ask your question?
Yeah, sure. I was just, I'm sure this is in the paper, but I missed it in the talk. So early on in the summary, you said something like, you're winning on small node sizes. So I think with 3 replicas, and then you said something like we're comparable with 5 nodes or with wide area networks. I'm curious why there's that distinction, right? And why maybe if you could describe why you're not performing as well when you increase the replica count.
So that's one way to say that's kind of like a major disadvantage of Rabia if you want to deploy that on a multi-data center setup or in a wide area network setup. So because Rabia requires all-to-all communication between the nodes, so that's kind of like and the message complexity of randomized protocol also contribute to that. So if we have like more than 7 nodes, or we deploy the servers across multiple data centers, so the round trip time is way larger. The performance will be seriously impacted.
Okay, thanks.
Okay, and thanks everyone for attending this session. I think we have a little break before the next session. Enjoy the rest of the conference.